In this example, we're going to draw a very basic bounce diagram and then also take a cross-section and plot the corresponding voltage. And so this will cover the most basic problem type of the DC into an uncharged transmission line. One of the other things to keep in mind is that you may need to do this bounce diagram for the current instead of the voltage, but the same principle applies. You just put down all the I's instead of all the V's. So let's just start with our standard transmission line picture. We have a generator. I think all of you will be really good at drawing this before the semester is over. We have a load, and we also want to, so the name of the game is to draw the bounce diagram. So bounce diagram for 0 to 3t, and then also plot the voltage at z equals 1/4 d as a function of time for that time period. And we also give you the basic values. So Zg is going to be equal to 50 ohms, Vg is going to be equal to 10 volts, C0 is going to be equal to 75 ohms, and the load is going to be equal to 100 ohms. Now, so again, let's start out by finding the initial parameters. So V plus is going to be equal to a voltage divider between Vg, between the transmission line and the generator impedance, which is going to be 10 over 75 over 50 plus 75. And that's going to give us an initial input voltage of 6 volts. And then in the current in this case would just be V plus over Z0, which would be 6 over 75. This is right, 75 there. So that it's handy, and that'd be 0.08 amps. Now at the load, the other main thing we want to find is gamma L, which is going to be equal to ZL minus Z0 over ZL plus Z0, new minus old over new plus old, which is going to be equal to 100 minus 75 over 100 plus 75, and that's going to be equal to 1/7. And then at the generator, the other key parameter we need to know at the generator, it's going to be Zg minus Z0 over Zg plus Z0, which is going to be equal to 50 minus 75 over 50 plus 75, giving us a reflection coefficient of 1/5. So these, if we're just looking at the voltage, these are the main pieces of information you need. So let's just also calculate out the other voltages we need. So the initial reflection, we'll just do the voltages here for simplicity's sake. It's going to be the reflection coefficient times V plus, which is 1/7 times 6, going to be 0.857 volts. And then it's going to make its way back into the generator and get reflected. So that's going to be gamma G V minus, which is going to be minus 1/5 times 0.857, which is going to give you minus 0.171. And then that should go, and then, well, let's just calculate the currents, even though we're not going to draw them in this case, but just remember that the reflected current is going to be equal to the reflected voltage, but with a negative sign, or else you'll make me cry. And that's going to give us 0.857 divided by 75, which is going to be minus 0.114A. And then the corresponding positive current is going to be equal to V++ divided by Z naught. No change in sign here. So 0.171 divided by 75, which is you're going to find is going to be equal to negative 2.3 milliamp. So 10 to the minus 3. And so let's just start by drawing our bounce diagram now that we're armed with this information. We only want to make it to 3t, so we don't have to go that many times. 2t, 3t, and it's going to bounce back and forth with one way trip per capital T of time. And let's write down. Let's just look at, in the case of the voltage, we're going to write down what the elevation change is every time you cross this line. So in this case, it's going to be plus 6 volts. This is going to be 0.857, and over here this is going to be minus 0.171 volts. And then the second part of the question, so this is the first request is to draw the bounce diagram, and then the second question is to plot how the voltage changes at location Z equals D over 4, so a quarter of the way in. And so again, we do that. We're gonna draw that line across, visualize. We're gonna add and figure out what the voltages are in terms of the elevation of these. So over here it's 0. Over here it's 6 volts because you cross this 6 volt line. And then next up you cross this line, so this triangle is at 6.857. It's the initial elevation plus that change. And then you cross this line, which subtracts minus 0.17, so you're left with 6.69 volts. And so now you have the elevation for all of these triangles, and you just have to plot out what this slice will look like. So as a function of time, if you lift out, this is going to be 1/4 t, and then this is 1/4 t here, and then over here this is going to be 3/4 because it was 1/4. It's 1/4 big T from reaching the other side, so this is going to be 3/4 t, and then you're going to have another change at 1/4, 2/4, so 2/4 later, which is going to be 5/4t, and so you can start plotting this. So it starts out at 6 volts, and then it goes up to 3.87, so that corresponds to this chunk here, and then over here it comes back down here. So this value is 6.69, this value is 6 volts, and this value is 6.857. So actually this value is still higher than the original, so to be really accurate, the line should be somewhat more like that. And so what you'll see is that it's going to, every time it bounces back and forth, it's going to perturb a little bit, but the amount that it perturbs by is going to decrease over time, and eventually it's going to settle into steady state. And the steady state is just going to be the situation where the transmission line disappears. So the final thing that it's going to settle at will be equal to Vg, the voltage divider between ZL plus Zg, like your regular Kirchhoff's voltage law result at t goes to infinity. Probably didn't ask for that, but I think it's also something good to re-emphasize.